Okay, so another way that diodes can become non-ideal is if there's Shockley-Reed-Hall recombination generation centers contained inside the depletion width. So we've looked before at this expression for Shockley-Reed-Hall recombination, but it turns out it's actually also equivalent to a generation rate when the concentration of carriers is smaller than Ni squared. So we're going to assume in the depletion width that the NP product is actually smaller than this, and then see what happens. So now defining terms again, the Cn is the thermal velocity of the electrons times the capture cross-section for electrons of this hypothetical trap we're putting in, and similarly. So we're going to look at the band diagram for the p-n junction, and we're going to put in this trap level in this sort of special way. It turns out that E trap equal to EI maximizes this recombination rate. So this will be a worst case scenario assumption. Here's our depletion width, and I'm going to point out that this does depend on voltage. Okay, so the intrinsic Fermi level is approximately at E gap over 2 inside the band gap. And that'll have some consequences in a minute in terms of the temperature dependencies of the diode current also. Now further, we're going to assume, so we're assuming here that E trap equals EI. We're also going to assume that sigma n equals sigma p and V thermal n equals V thermal P. Under all those assumptions, we can go through here and substitute everything in terms of the CNs. We can replace these N trap and P trap terms. Now remember, our definitions of N trap and P trap are N when EF equals E trap, and under this assumption that's in the middle, that's at the intrinsic level, that means it also equals EI, and so NT and PT both become NI. Now furthermore, inside the depletion width, N equals 0, N naught equals 0 and P naught equals 0. So if we assume low injection also, that means that these can go away. And let me bring this down and rewrite it. So we've got Cn squared N trap minus sign overall Ni squared over Cn times Ni plus Cn times Ni. Okay, so we can cancel out some Ni's, and we can cancel out some Cn's, and we are left with a negative Cn N trap Ni. Now, if we go back one step and break this assumption a little bit, that the sigmas and thermal velocities are the same, we could modify this a little bit and end up defining a T naught effective equal to, tau effective tau naught n plus tau naught p over 2. And then bring that back into this expression. But what we're going to do here is just assume that under these expressions, tau n naught equals tau p naught. And if we remember our definitions of tau n naught and p naught, it's actually 1 over this. So we end up with negative ni over tau naught effective. So at the end of the day, this u becomes negative, and if because generation and recombination have opposite signs, this turns out to mean that this recombination center that we've considered in a normal region of semiconductor inside a depletion width will become a generation center. So really the relevant thing it does is start thermally generating carriers, electrons and hole pairs inside the depletion width. And then once they get into the, once they're introduced into the bands, they'll drift to the other side. And so there'll be a Jn, a current, and a Jp, a hole current. So the total amount of current we can estimate because G, or U in this case, has units of number per centimeter cubed per second. If we multiply this by an area, by a length, so G times WD is going to give us a number per second per centimeter squared. And then if we hit it with the electron charge, now we've got coulombs per second per centimeter squared, which is equal to amps per centimeter squared, which is our units of J. So after doing our dimensional analysis here, we can see that the J naught caused by the Shockley-Reed-Hall generation inside the depletion width is going to be equal to Q Ni over some tau effective, which is a mixture of the N and P type minority carrier lifetimes, times our depletion width, which is a function of voltage also. So this is a little different than the ideal diode leakage current expression because of this voltage dependence here. So really what we would conclude is that if we only had Shockley-Reed-Hall reverse bias current, the current would not actually saturate. It would keep going with reverse voltage. Now, the other thing that we want to look at is the temperature dependence of Ni here. So it turns out that because Ni instead of Ni squared appears in this expression like it does for the ideal diode, the temperature dependence is exponential to the negative E gap over 2 kBt here. And then also it turns out to introduce a similar factor into the diode current expression. So when we put the whole thing together, the JV contribution from Shockley-Hall recombination inside the depletion width is J naught. So for the ideal diode, we effectively had a factor of 1 in the denominator here. In the non-ideal diode, we can introduce the idea of an ideality factor, which becomes greater than 1. So we can define an ideality factor of J equals 1, neta equals 1 for ideal. And then anything neta greater than 1 as non-ideal. So in this case, for recombination inside the depletion width, we get an ideality factor of 2.